Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, CEO for C-Therm Technologies. C-Therm are the representatives for Metravib, ACOM, DMA in North America. We're very proud to be associated with the Metravib brand, a premier capability in DMA characterization. Today's webinar is going to run for approximately 50 minutes. It's being recorded. It's a shareable piece of content. So if you've got friends or colleagues that would be interested in this, please feel free to share with them the link to the recording. You'll receive that automatically after the webinar concludes. Today's topic of discussion is on the importance of DMA, dynamic mechanical analysis, testing in bringing hydrogen and electric vehicles to market. We are very excited about this webinar presentation. It really complements nicely a lot of the work we're doing in thermal connectivity in these application spaces. It's remarkable for us. We've been in material characterization for approximately 20 years, and these alternative transport alternatives to ICE vehicles have been worked on since that time. But you know, what's really remarkable is just the shift in intensity and urgency in getting these to market. You're seeing groups like Ford announce that they'll be offering all of their models all electric by I think 2025, 2026, in that time frame. Just the approach and how it's shifted, and that's just one example. Of course, there are many others that it's really clear that there's a once in 100-year transition happening in transportation as we move off of ICE. And this presents a lot of opportunity, but it presents a lot of challenges as well, as we're trying to accelerate time to market and ensure a robust product that will meet the warranty and product performance attributes that are so important that we hit. This creates a lot of pressure on the engineering and development groups in these organizations, and some of you on the line may be feeling that heat, that pressure of getting there faster. Time to market is certainly something we're hearing a lot more about, and the fundamental difference between these types of vehicles and an ICE vehicle is significant. So it really does require us to go back to some of the elemental components of the vehicle, from the tires, the chassis, the whole design, the heating and cooling systems, the comfort accessories and seating and other things. It creates a lot of challenge for material characterization and making sure that we're developing product that doesn't require a lot of iteration, that we can do our material selection in an effective and efficient manner, and ensure that essentially you get it first time right. So we'll be transitioning the discussion here to Dr. Michael Landry. He's going to take us through why DMA is so important in this work. I just wanted to offer a little bit of background on C-Therm technology. I see a number of familiar names and folks that have worked with us in the past, but some new names as well, some new contacts. And if you're not as familiar with C-Therm technologies, we're really niche specialists when it comes to thermal connectivity. So our own engineering team is really focused on advancing transient methods for thermal connectivity characterization. Our purpose is to advance these capabilities directed towards novel materials that are required for the future applications that are driving engineering challenges around the world. So a lot of that is the electrification of transportation, a lot of thermal management issues, and the transient methods we focus on are fast. So they're meant to accelerate the test time. The alternative to transient techniques is a classification called steady state. In steady state, these are measurements are taking typically a day to administer a single test. Well, with the accelerated transient testing we develop, we're talking a matter of minutes to get results back, and multiple results at that. So the latest news from C-Therm in new product development is the launch of Trident. This was launched about a year and a half ago. It's really exceeded our expectations. It's become very popular, particularly in the space of automotive, electric vehicles, hydrogen research. It brings together three of the most prominent methods for transient thermal conductivity. You see the different sensors available there. There's a single-sided sensor. There's a flex sensor, which is really good for anisotropic materials if you're getting into oriented materials. We're going to be doing a webinar in a few weeks with a group from the UK, and they're working a lot on battery packs and have some very anisotropic materials there, and how important that is to consider in the design of a battery pack, and ultimately how the thermal management is maintained. Potting compounds around the electric motors, another really good example, where the thermal conductivity makes a huge difference. So one insight we were able to put forth was that for every 1 watt per meter Kelvin gain in the thermal conductivity of the potting compound, it reduces the operating temperature of the electric motor by I think it's about 20%. And so huge gains in increasing the effective thermal conductivity of the potting compound. We have other webinars on these. AJ, I'll ask you to put a link into our most recent automotive webinar for thermal conductivity. We don't have time to cover that material today, so I'm going to keep moving, but if you have interest, I encourage you to check it out. This is a nice quote from a testimonial from one of our clients at Haydel, working in the automotive sector. They produce a lot of high conductivity polymer composites, and one of the nice parts of this statement is just what a key piece of testing equipment has become within their group. They're doing something really interesting with the single-sided MTPS sensor. They're thermal mapping this composite, because they understand that the quality of the dispersion in that polymer matrix is one of the issues that can be encountered in terms of really improving the effective thermal conductivity. And this is something we've seen a number of cases on, that it's so important to get a good distribution. And sometimes you'll see agglomeration with the filler, you'll get settling, but you have this unique ability to pick that up and detect it with the MTPS sensors. I really appreciate the opportunity to work with Haydel Composites. They're doing some really great stuff, and I think really pushing the capabilities and improving high conductivity polymer composites. Great group to work with. Now, Metravib is a partner of C-Therm's. We represent Metravib. Metravib is part of the ACOM group. They're based in France. Really excellent group and leaders in the world in DMA characterization. So they have the most advanced platform when it comes to high frequency, high force. If you're looking to really have the best piece of equipment for your lab when it comes to DMA, if you want to look at crack growth, if you're looking at high volume throughput, if you want to, particularly for tires and rubber and more advanced composites in vehicle systems, as I think you'll see as we take you through the presentation, we're very proud of that association and partnership with Metravib. C-Therm is a premier provider of thermal conductivity instrumentation. So it's significantly technically differentiated. It offers unique innovation in the measurement, advancing the transient, high-speed measurements, high accuracy, really high sensitivity. And we look to associate with other groups that are really pushing the boundaries in material characterization. And our association with Metravib is something we're very proud of in representing them within North America. These are some of their clients you see listed here. So you can see a broad range of groups here. A lot of polymer, composites, rubber, tire, automotive companies. And you can get a sense of some of the different application areas in looking at these names. I'm sure a number of you are recognizing these different groups. So I've taken up maybe more than my time. I'm just the warm-up act. I'm really pleased to introduce my colleague, Dr. Michael Landry. Dr. Landry completed his PhD at McGill University a few years ago, worked on biomaterials. In that research, was quite interested and did a lot of application work with DMA in looking at the mechanical stiffness of these types of candidate materials. Joined C-Therm several years ago and is risen to the role of senior scientist here. Michael does a great job working with clients, consulting with them on DMA's application, as well as some of the other thermal conductivity applications we offer, and has put together a really great orientation on why DMA is important when we're looking at hydrogen vehicles, as we're looking at electric vehicles and different hybrid options. So I will happily pass on the speaker spot to Michael here and ask him to bring up his slides, and I will rejoin you fine folks for the Q&A session at the end of the presentation. Thank you, Michael. You want to take it from there?
Sure can. All right, thank you so much, Adam, for those kind introductory words that you had. It's always been a pleasure to work with you. Today, I'm going to be going through a bit of a topic that's quite close to my heart, which is bringing emerging technologies such as hydrogen and electric vehicles to market in a fast and rapid fashion. And this is done through precise and safe material design using DMA as a heart technique for us to design and test these materials themselves. So it doesn't come to a surprise that when we're talking about alternative technologies for automotive, some of the prompt and detail of this is global warming. Since the 1800s, we've been noticing CO2 levels have been increasing over time. And as a result, global sea levels have increased and intensities of storms have increased. And this is going to be an impact that we're going to see on our daily lives every single day. And it's a problem that we're going to see, and it's going to impact our lives. So we want to do something about it. It's a global call to action, as you will, to try and reverse these effects. Now, one way that we can reverse these effects is to target some of the culprits that are creating the most emissions. And when you look at some of the top offenders for these emissions, and break them down into sectors such as transportation, industry, and electricity. One of the top contenders is electric vehicle, or is transportation. If we break that transportation out, about 58% of it is personal vehicles or light vehicles for transporting us from work to different errands to doing our daily lives. The majority of these emissions are being emitted by traditional internal combustion engine powered vehicles. So there's quite a bit of an urgency in the market for this. Not only is it a problem that the world is facing, that individual consumers are concerned about, but government agencies are becoming concerned about this. The EU has suggested a date to the end of the combustion powered cars around 2030 to 2035. Not only are government regulations and government agencies declaring regulations towards these the sales of these vehicles, major car manufacturers are already starting to make the switch so that consumers can make smart decisions to influence the future and reduce carbon emissions. So some of the car manufacturers that are planning and have made pledges already to do this transition are big brands like Jaguar, Bentley, Cadillac, Lotus, BMW, Volvo, and they've all pledged to make the transition around between 2025 and 2030. Additionally, some of these car providers or automotive manufacturers are becoming even more aggressive with their transition. So Ford has suggested that they will go all electric in Europe around 2030, and also offering all of their models either in an electric or hybrid model by 2026. So we can see that there's quite a bit of urgency in the market and quite a bit of a fast transition. Like Adam said, once in a century transition from one technology to another is what's currently happening in a rapid sense. So there are quite a few emerging technologies that are there to help bridge the tremendous technological gap that we're about to make. And one of them is the hybrid gas electric vehicle. This is a bridging technology, meaning that it has some of the benefits of internal combustion engines, such as longevity for travel, but also has some of the benefits of zero emissions for short duration travel, such as from work to home or home to work, getting groceries and whatnot. For longer trips, it would switch over to a backup source like gasoline, and you would be able to continue on your journey. Some of the more aggressive alternative technologies are those like the hydrogen fuel cell electric vehicle. This uses hydrogen as gas as a source fuel for powering the engine, usually through a fuel cell technology and a redox reaction occurring. Finally, there's the all-electric vehicle, which is probably one of the more widespread technologies right now. You can see these in the form of Teslas, in the form of other type of fully electric vehicles. These use battery technology to power a DC converter and give you power as you go. Now, as we're transitioning from one technology to another, we've had about 100 or so years to figure out how to safely design these materials, how to iteratively design materials that are inherently safer for vehicles through iterative design. We've had a long time to change and to refine each of these materials. But with such a dramatic change in the market and towards all of these new modes of transportation, such as hydrogen and fully electric vehicles, there's such a short time for us to get things right, for us to have those high safety standards that we have, but in employing these new technologies themselves. So some of the concerns lie in the heart of these technologies, such as the hydrogen fuel tanks in the hydrogen fuel cell electric vehicles, or the actual fuel cell stack itself, which can have detrimental impacts if things are designed incorrectly. In such a technology that is very mobile and prone to vibrations, to tire rotation and bad road conditions, these materials that are being developed are under a dramatic amount of stress and strain, which we need to account for when we're designing these materials. Additionally, safety concerns are a paramount feature for some of the all-electric vehicles. Because of anode materials and separators, cathode materials that are typically designed for less mobile technologies, when they get used in an all-electric vehicle, they may be found to see some side effects from being vibrated constantly or having such harsh conditions under heat and cold. So we need to be able to design these new materials to alleviate some of the disastrous things that can occur. We, as a material scientists, we have to realize that these materials that we're designing for the future have personal consequences if they're wrong. So we're not only designing new batteries for technology for these cars, but these cars are being driven by consumers, which are at the front line of the users for these vehicles. So we have to get it right the first time. So in such a dynamic system as a car, something that is constantly vibrating, something that is under heat and stress and different frequencies and being driven constantly and used every day, we need to get a sense of how these materials perform under stress, strain, heat, cooling, and other atmospheric effects. And one of the best techniques to do that is through DMA. So I'm going to give you a quick little oversight, little basic training for DMA. So DMA, or dynamic mechanical analysis, is one of the most accurate techniques for determining the viscoelastic properties of a material. Viscoelastic properties are more or less the viscous component of a material and the elastic component of a material. And these are typically intertwined in a complex stiffness in polymeric materials or rubbers. DMA, basically the way it works is that we have a sample that's pinned between a force transducer and a displacement transducer. Upon a dynamic excitation or cyclical excitation of a specimen, usually performed by an electrodynamic shaker, we can measure the force and the displacement of these samples. Through displacement and force measurement, we can get an accurate determination of the complex stiffness of a material itself. So the stiffness or the complex stiffness is given by the force over displacement. And therefore, additionally, the force and displacement which are measured can also be manipulated with a phase difference to give tan delta. Tan delta is equal to the loss modulus or the over the storage modulus. Loss modulus is the dampening effect of the complex modulus. It's usually proportional to some of the intrinsic friction within the material, leading to heat loss. And the storage modulus is equal to the ability for the material to store this energy and release it in an elastic sense. Additionally, these are related for shear as well through these equations right here. So when we have a vertical dynamic excitation, we can convert this into different excitation modes through the sample geometry itself. So we can do this through tension, a uniaxial tension experiment, compression through compressive forces on a material, shear, which is one of the more used for tire applications because you get 100% transformation of the shearing force into the material itself, or bending, which is more apt to fatigue type testing. So because we have all of these different types of sample geometries, different excitation modes, different frequencies, temperatures, this makes DMA very applicable to a large range of materials for testing thermoplastics, rubbers, metals, ceramics, films, paste, and other liquids as well. So I'm going to give you a quick example of some of the typical viscoelastic properties of response. More or less, this is what a typical rubber would look like for the loss and storage modulus with respect to temperature. So with temperature, we see 4 distinct regions of DMA when you scan through the temperature range and monitor the loss and storage modulus. We see the glassy region, which is typically dominated by the storage modulus. This is characteristic of crystallites forming in polymers. As we heat up the sample, we have a transition region, which is dominated by the glass transition temperature and also dominated by the loss modulus as well, spiking. After that, and we heat up the sample a bit more, we reach a region which is called the rubbery plateau, which is heavily dominated again by the storage modulus itself, followed by a terminal region, which is the complete loss of the storage and loss modulus and creation of a viscoelastic liquid. So with those basics, I'm going to bring you through some of the papers that I've selected for, and some of the work that has been done using DMA, particularly Metravib equipment. Now, the first paper I'd like to highlight is was completed by Anne Mainaldier in France, and it is entitled Mechanical Assessments of Hydrogen Storage Container Components. Its title is also in French because it was available mostly in French, but I translated it here for you guys. So Um, what they were trying to observe in these types of experiments, their focus on their work was looking at the hydrogen storage tank and hydrogen fuel cell electric vehicle. Now, typically these are called Type 4 hydrogen storage containers, which consist of a few different components. One of them being the carbon fiber composite material, which provides a lot of the strength for the handling of this hydrogen gas. Additionally, there's a high density polyethylene liner, which is more or less what seals the hydrogen inside of these tanks. Now you can imagine that these have to undergo dramatic pressurizations and depressurizations, constantly filling and defilling as it provides hydrogen to the fuel source stack. These have to undergo multiple cyclic pressurization cycles, and therefore they're extremely tested for their burst time, their burst pressure. And as we're trying to extend the range of these vehicles, we want to have more and more hydrogen that's available for these tanks. So we have to design materials that are more elastic, that are able to be stronger to hold this pressure in. A failure of one of these tanks would result in either a fire for the car, which is obviously not a great thing, or just dramatic loss of the vehicle completely through loss of fuel. So it's very important for us to get this right. So the researchers looked at particularly the composite material itself. They looked at creating these carbon fiber and reinforced epoxy resin materials. And they wanted to look at typically what would be done and a methodology to increase its strength. One methodology that was suggested in literature was a rapid cooling technique, where they rapidly cool the polymer after the epoxy resins after curing for 2 hours. Typically, the typical polymerization is a slow and steady rise of about a degree per minute, whereas this rapid cooling consisted of up to 20 degrees per minute cooling of the material itself. So they created these materials either rapid cooled or a typical polymerization cycle, and they looked at their Young modulus. They looked at the deformation with respect to the Young's modulus, and basically found absolutely no significant difference between each of these polymers that they made. Which is good, but they realized that these are constantly under dynamic pressurization and depressurization. So they wanted to look at cyclic effects of this using DMA. So upon using DMA, they noticed, and doing frequency sweeps of the material and holding the force constant, they noticed that the materials that were rapidly cooled had a 15% increase in the elastic modulus. They attributed this 15% increase to the diminishment of little cracks inside of the material itself. And they were able to prove this using SEM measurements as well. So some of the conclusions from this paper are that typically when you're designing these composite materials that are designed to be under dynamic stress and dynamic strain, traditional static methodology is not adequate enough for us to look at the modulus. And only DMA itself is able to elucidate differences in the microstructure of the polymer material. So they were able to elucidate a better technique for creating these Type 4 hydrogen storage containers, which were 15% stronger than their typical batches. And this was attributed to a difference in the microstructure of the polymer, which was elucidated by DMA. So the next paper I'm going to be talking a bit about is looking a bit more on the hydrogen storage side, but on the proton exchange or the fuel cell source itself. This work was entitled Titanium Dioxide Graft on Graphene Oxide Hybrid Nanofiller for an Effective Low-Cost Proton Exchange Membrane. And this was work that was led by Isabella Nicareta from Italy, and Luigi Coppola from Greece. So just some collaborative work that was done between the two of them. So typically in the hydrogen fuel source cell, we have a stack up of multiple different components. We have a catalyst, which are an anode layer, and a cathode layer, which has some catalytic converters in it. And hydrogen gas will flow through on one side, and during the redox reaction at the anode, we have transition of the of protons across a proton membrane. This membrane is super susceptible to thermal mechanical effects, thermal chemical effects, and also just generally mechanical effects from having such dynamic stress put on it during the movement of a vehicle. Now, typically, the industry standard material that's used for this is naphthalene 212. Naphthalene 212, which is this little polymer here, pictured at the top, is a very good high proton conductivity material, which has pretty good mechanical strength and resistance at room temperature. Under operating conditions, though, naphthalene, or naphthalene, sorry, has some detrimental effects where it has a problem with losing water at 120 degrees Celsius, which causes a detriment for the performance of these proton exchange membranes. Water is an essential requirement for these polymers to hold onto during the extent of their operation. So it's important for them to have this. Additionally, these polymers are quite environmentally problematic. They involve high degrees of fluorination reactions, which are very environmentally detrimental. So what they looked into is some sulfonated polymer, and more or less doping these sulfonated polymers with graphene oxide and titanium dioxide nanoparticles. By varying the amount of these dopants into the sulfonated polymers, they're able to achieve various degrees of proton transfer in these stack-ups. They wanted to look at the thermal stability of these materials by performing DMA, by monitoring tan delta in DMA experiments, by sweeping a temperature from around room temperature all the way up to about 250 degrees Celsius. What they noticed is a dramatic shift with increasing dopants leading to higher thermal stability and much higher thermal stability than that of the industry standard. Additionally, due to the addition of graphene oxide, this was shown to enhance the storage modulus of the material at higher temperatures, reaching upwards of 200 degrees for a very thermally stable and more mechanically robust material than the existing naphthalene 212. So this is more or less what they did in the stability of the work. I believe currently they're moving on to doing more robust experimentation to bring this platform to the industry. But what we can learn from this is that these new graphene titanium-based materials are more mechanically robust and thermochemically stable. And this is attributed mostly through these DMA experimentations, which are able to highlight the differences between these new and emerging technologies. Additionally, using another thermal technique called TGA, we're able to see that these are able to hold on to water a lot higher than the existing material itself. So this is pretty exciting breakthrough on the part of this Italian-Greece team. The next topic I'd like to quickly go through is some strategies that we're looking at battery technology, particularly sodium-ion battery technologies, and the importance of stability for the anode, in particular transferring to a black phosphorus-based anode. This is work that was conducted again in Italy from a large group of researchers there, particularly in the National Research Center for Electrochemical Storage. So by nature, the batteries under load typically have a dynamic system where the anodes can have the anode and the cathode. We have transmission of lithium ions, or in this case, sodium ions, across an electrolyte, which is guarded by a separator in the middle. Now, during the extent of dynamic electrochemical processes and under stress from mechanical vibrations, what can happen is at the anode, we can have small cracking, and this cracking and transfer through the electrolyte can create solid electrolyte interface growth, which grows from the anode towards the cathode, breaking the separator and ultimately creating a failure in the battery itself. Now, what this group did is they looked at using an inspiration from nature, these newly synthesized hydrogen bonding type materials, to encapsulate some of the anode and create a barrier so that it is able to self-heal and prevent this growth from occurring from one side of the anode to the other. So what they did is they created these new formulated self-healing anodes from hydrogen bonded sulfonylurea, I believe, type polymers. And they were able to do some formulation, creating two different formulations that they tested, either 50-50 mixture between these polymers or a 40-60 mixture between the two polymers themselves. And they were able to do some DMA testing by sweeping the frequency and measuring the G prime, or the elastic modulus, during the experimentation. Upon taking some pristine samples of the materials, they found that they had an elastic modulus that was pretty decent, around, I believe, 100 megapascals. But after going through a heating process about around 50 or 40 to 50 degrees Celsius, these polymers are able to reheal and re-solidify and rearrange to create a material that is even more mechanically robust than the previous pristine material. And this was found to attribute to an anode being much more elastic, and attributing to higher elastic modulus and lower loss modulus in the material itself. By sweeping the temperature, they're able to see that these polymers and anodes behave very interestingly, where we have a decrease of G prime, or we have an increase in G prime upon heating, and a decrease in elastic modulus upon heating, and then an increase back to the same level upon cooling, meaning that these are mechanically robust upon heating and thermomechanically stable as well. By doing stress strain curves and doing some cutting experimentation and looking at the way these materials self-heal, they're able to show that both 50-50% blends of these polymers have a higher tensile strength after self-healing, but the 40-60 versions of these anode type materials just ascertain the same modulus over time, showing how dramatically improved these mechanical behaviors are compared to the existing technology. So hopefully from this, I was able to show you that we're able to numerically determine recovery mechanical strength using DMA, and that we're able to ascertain some intrinsic differences between the thermomechanical and mechanical properties of these different formulations, and how it's super important for us to do cyclical thermal testing at temperatures so that we know how these materials perform at the temperature of operation rather than at room temperature itself. Final thing I'm going to be touching on today is designing new tires for electronic vehicles. So some of the tires themselves, because because the intrinsic nature of these new electronic vehicles, which have a higher torque for the engine, an instantaneous torque as compared to the traditional internal combustion engine, which has transmission, which reduces torque at the very beginning, we have some demands for the new rubber materials for these electronic vehicles. Multiple consumers, automotive industry are trying to transition some of these formulations to create a higher grip on the pavement, a lower roll resistance, quieter tires, so that that these perform as well or better than their existing technology. So one of the more interesting components is a lot of the electronic vehicles that are on the market today have specific tires that are formulated to have a very low roll resistance. Because typically if you use regular tires on these systems, you have a decrease in mileage of around 20 to 30%, which is pretty detrimental when you are with these emerging technologies. Additionally, these materials have to be quieter when they're rolling. The internal combustion engine itself would typically determine the noise level of a car, but in this case with the electronic vehicle or the electric engines, this is not a concern as much anymore, and it's more or less determined by the tires rolling on the surface. So if we want to create a quieter system, we need to focus on higher the intrinsic volume of the tire as it rolls on the ground. And this has always been something that has been on the concern for tire formulators, where people are using and playing with different additives such as silica and carbon black to have dramatic effects on these characteristics. So typically this is characterized by tan delta, which will provide some insight into two things. Usually the wet grip, the higher tan delta will lead to a higher wet grip, whereas a lower tan delta will lead to lower rolling resistance. We're able to tune these by using different additives in either silica or carbon black to increase the wet grip or decrease roll resistance. And this experimentation is completed by using shear excitation on different tire formulations. By tuning the additives in these tires, we're able to change where the wet grip will occur. So tuning it to have a lower wet grip for winter tires, or a more plateau in the middle for an all season, or even a higher wet grip for a summer tire. And all of these different formulations are able to be played with by measuring tan delta over a temperature scan. Provide mostly a tuned tire for your for each of the weather events that you're experiencing. So just for some conclusions here today, I just wanted to reiterate that designing these new materials is super duper important for us when we make this transition from non-IC, from internal combustion engines towards electronic and hydrogen-powered storage materials. As we make this transition over to these alternative technologies, we need to do this in a rapid sense and in a way that is much more safe for the consumer. And with safety being a particular paramount concern for dealing with high flammable gas like hydrogen. And just in general for electronic vehicles, these battery materials have to be tested under a dynamic strain because of vibrations occurring in the tires or in the vehicle itself during your voyages from the back and forth through your life. And I hope that I was able to show that dynamic mechanical analysis is an ideal method for testing these dynamic material responses and designing rationally new materials for the future of these technologies. Now, with that being said, I'm going to quickly go through a little bit about Metravib and what makes it so special for designing these new materials itself. Metravib is like Adam was saying, the leading manufacturer of high-end DMA equipment. They have three product categories. Their desktop series, which is mostly low force DMA. Their high frequency analyzer with capabilities up to 10 kilohertz. And then their DMA Plus series, which is basically a DMA plus more, because you're able to get access to high force DMA, automated DMA, and fatigue testing as well. So under high force DMA, we have DMA plus 300, 1000, and 2000, which is the peak to peak load that's able to be provided. So 2000 newtons peak to peak for the DMA plus 2000. Additionally, we have access to Expander, which is able to do automated testing 24/7 in your lab on compression, tension, and shear testing of materials. And finally, we have fatigue testing, which is in the form of heat buildup testing, crack growth, and crack growth testing, which are methods that I will explore a little bit more in this talk. So what sets Metravib apart from other DMAs? One thing that sets us apart is the rigidity of our test frame. The rigidity of our test frame, or the essential condition for performing DMA is that whatever you're measuring the sample needs to be much more stiffer than the sample itself. So because of this large difference in this very stiff test frame, we're able to measure a large range of stiffnesses. So the measurement domain is 6 decades on DMA plus 1000, 2000, and 7 decades on DMA plus 300. Whereas more classical DMAs are able to only be limited to around 3 to 5 decades of measurement. So you are able to have a larger range of stiffness that you're able to measure on these materials. What else separates us apart is the large amount of specimen holders are able to support a wide variety of materials. So rubbers, reinforced polymers, bitumens, generally polymers and fibers, films, metals, alloys, glasses, ceramics, anything under the sun we pretty much can test, either through compression, tension, bending, or shear, which is super important when you want to design new materials for the future. Additionally, one thing that sets us apart is the single load cell which is present. So we have a load cell that does not need to be changed out during experimentation, and this was rationally designed with Expander in mind, so that we're able to test a wide variety of stiffnesses using Expander without changing out the load cell over time. So Expander is able to test your shear, your compression, and other samples only by changing out the actual sample holder once it's completed an entire one type of its sample itself. What else separates us apart is crack growth. So crack growth is one of the more hot topics that we've had a few webinars about. So if you're interested in crack growth, I'll leave it to some of the recordings to talk about. This is method it was developed with Michelin in mind. It's able to measure up to 4 simultaneous cracks. And more or less what happens is you have a camera that's focused onto the material itself. You have a specific shear energy that you're applying to the sample. For stabilization, you can cut into your sample and then watch using the camera the crack propagate. By plotting crack growth rates versus some shearing energy, you're able to get a sense of how your material is going to behave, either through using multiple different types of excitation profiles, such as sine, Haber-Sine, or complete wave control. In the case of designing tires, we're able to modify the wave control feature so that you can excite at a different frequency or custom frequency, or through oxygen control rates, which are able to provide different oxygen rates to the system to tune that capability itself. And with that, I'd like to thank you for your attention today. If you have any questions or anything, we have a Q&A session that's going to be here. Additionally, if you have any questions or that we don't have enough time to get into today, or you have to get running at some point, we have info@ctherm.com, and we can set something up, or you can give us a quick call. I'm just going to highlight a few other resources that we have. We have an extensive webinar collection online, various different topics like crack growth or other thermal conductivity products as well that you can look through. And then, as well as a large tech library, which is searchable for featuring a lot of our own thermal conductivity instrumentation as well. I'm going to let, actually, I will give you a quick plug here. If you're interested in anything that you saw today and you want to take the next step with us, you can get a hold of us either by searching us at ctherm.com/Metravib, sending us an info@ctherm.com, and we can either book a discovery call, video demo, we can get some testing done, or just walk you through any information that any questions that you have associated with DMA. I will highlight our next webinar coming up, which is a webinar involving Martin's Rubber Company, improving heat dissipation of submarine network repeater enclosures with novel filled materials, presented by Dr. Isaac Watson, and should be on September 22nd at 10 a.m. EDT. You can either register at this website right here or message us in the comment box here, and we will get you started with the registration for that webinar. And I'm going to pass this back to Adam if he has any sort of comments before we start the Q&A session. But it's been a pleasure to talk to you guys about DMA.
Excellent. Thank you very much, Dr. Landry. Greatly appreciate it, and wonderful job as always on curating the content for this this presentation. At this point, I'm going to close the recording. We'll keep the line open for the Q&A session, but I will take this opportunity to also echo the thanks that Michael expressed to the audience. If you're viewing this live with us online today or taking the time to review the material as a recording, very much appreciate the opportunity to share a little bit about the good work that Metravib is leading the way in terms of DMA's application on these types of materials. And as Michael expressed, we hope this is something that may lead to further discussions, and we'd be happy to pick up on a one-on-one basis, a technical consultancy on your needs and advising on what capabilities match up, what limitations are there in terms of applying DMA for your specific needs and requirements, and bringing new materials or new product to market. So with that said, I'll stop the recording. Thank you very much, and stay on the line if you'd like to participate in the Q&A.